the stable ones by Fomin-Kirillov. And what we are going to do today is we are going to sort of combine the crystal structure for the Stanley symmetric functions that I defined last time with some crystal structure on set value tableau by Monical, Pechenik, Scrimshaw. But what we are actually going to do is we are going to mimic sort of the setup from last time, where we looked at certain decreasing factorizations, and we actually want to define the crystal structure on these decreasing factorizations. But we will get some intuition from the crystal structure for the ones indexed by partitions. Okay, and then last time I already introduced the zero Hecke monoid, which is, you can think of as sort of very similar to the symmetric group. So the relations are basically the same, except that if you take, let's say, a simple transposition Si and you square it, in the symmetric group, you would be getting 1, the identity. But in this case, so now I'm not writing simple transposition, I just index everything just by a number. So in this case, P is equal to P. So it's an idempotent. But other than that, you have the braid relations, and then you have the commutation relations when things are far apart. Okay, so I already went over the examples last time. And then just to remind you of the setup, so what we are now going to do is we are going to take some word in the zero Hecke monoid, which is now just a word in the letters from 1 up to n. And then we are going to, again, like sort of factor it into factors, and each factor has to be decreasing, meaning the numbers in that factor have to be decreasing, strictly decreasing. And then the factors we are going to denote by hm to h1. So if we have m factors, then that would be the factorization. And I'm going to denote the set of all decreasing factorizations by this HMW. And here's an example. So if you, for example, take the permutation 1, 3, 2. So by this I now mean S1 times S3 times S2. So this is now not the one-line notation. This is viewed as a product in the simple generators. But for example, this word, forget about the brackets, right? 3, 1, 3, 1, 2. That's equivalent to 1, 3, 2, because you can move this first 3 across the 1, and then the 2 3s would collapse to 1, 3, and you can move this 1 over, and 1 times 1 is also 1. So this word, if you forget about the brackets, is equivalent to 1, 3, 2. And then you can see that this one has been sort of factored into decreasing factors. This one is decreasing because 3 is bigger than 1. This one is also decreasing, and a single entry is always decreasing. And we also, I should remind you, we allow empty factors too. So here are just examples of decreasing factorizations of this particular word. Okay, and then we defined last time the stable Grothendieck polynomial as follows. So it's indexed by a permutation. Then we look at all possible decreasing factorizations. And we write it in terms of monomials by saying x1 times the length of the first factor, x2 times the x2 to the length of the second factor, and so on. And then this parameter beta basically keeps track of how many letters we have added from the reduced case, right? So if W is a reduced word for this permutation, in the zero Hecke monoid, things can become arbitrarily long, and this beta basically just keeps track of how far away we are from the reduced case. Okay, and then I think I already talked about this also last time. So if we take the same W again, then these would be the decreasing factorizations for the constant term. And if you basically add them all up, then you get this monomial down here. The red part comes from these two, and the blue comes from these two, and that gives us a Schur function S21. Okay, and then of course you can do a similar thing for the higher order beta terms, but this is just an example. And there is already a theorem by Fomin-Green which says that these stable Grothendieck polynomials have a positive Schur expansion. So remember, S lambda of x was the Schur function, and this is saying that you can write this as a sum of Schur functions, and you have some coefficient here. So the GW lambda turns out to be a non-negative integer coefficient. And then you have some power of beta. So this gives you a positive Schur expansion. And in fact, they even gave a combinatorial interpretation for these, which I don't want to emphasize too much. So SSYT just means semi-standard Young tableau of shape lambda prime. So lambda prime is just the transpose. And then you want that the reading word of this tableau should be congruent to your W. And basically what we want to do now is we want to sort of rederive this formula by putting a crystal structure on the objects that define these stable Grothendieck polynomials, namely these decreasing factorizations. And as we discussed last time, if you have a crystal structure on these objects, if you look at only the highest weight elements, meaning the ones that are sort of killed by the crystal operators EI, then if you count those, that would precisely give you the Schur expansion. And just in case you forgot, like for the crystals, we have these operators EI and FI, which are partial inverses, and they sort of give if you look at connected components, like everything that's connected by FI and EI, then that would actually give you something that gives you the Schur function. If you sum over all those things in a connected component, that gives you a Schur function. Is there a question or no? Okay.
I think Raghavan had a question.
Okay.
His hand is raised.
Do I need
Raghavan?
to do something? Wait.
No, just Raghavan,
Okay.
are you here?
Maybe his mic is not working or something.
No, it seems on.
Yeah, but on his computer maybe.
Ah, okay. Okay, maybe you can just go ahead on.
Okay.
Ah, I see.
Or
His mic doesn't seem to be working. Okay.
Oh, he can write it in the chat and then you
Yeah.
can read it out. I can't really see the chat, but if you can. Oh, chat two thing. Okay. Well, if he has a question, he can write it in the chat.
Yeah. Why don't you just go on?
Okay.
So he says, could we please look at the example again on the previous slide?
Okay.
So
Is there a question about this example? So I should mention, perhaps this is not completely clear, but here what I've written is only things with two factors. But of course, you can always put empty factors in there as well. And that's why, for example, there's an x3 here. So if for example, if I want to get this monomial x1 squared x3, then I can get that from this one by doing 1 then an empty factor, and then a 3, 2. And then remember, I label my things from right to left. So the 3, 2 has two things in it. So that would give me the x1 squared. Then I would have an empty factor, which would give me an x2 to the 0. And then this part gives me the x3 because it would be in the third factor. Does that make sense?
Sorry, you mean the 1 would be in the third factor?
Yeah, because I'm labeling from right to left.
Oh, yeah, okay.
So,
and the symmetry is not obvious from this, is it?
No, it's not obvious.
Yeah.
But once you have the crystal structure, because then because we can define these SI operators, which are reflections in the strings of the crystal, then you actually get symmetry automatically. But yeah, from this, it's not obvious.
Okay, so no more messages from Raghavan, maybe we can.
Okay.
He said his mic has some problem, so he'll just come back on he'll log in on a different machine.
Okay.
Yeah, you can just go ahead.
Okay, so if we use the theorem by Fomin-Green, then the Grothendieck polynomial for S1, S3, S2 would actually be equal to, well, there's S21, which we just saw before, and then beta times 2 S211 plus S22, and then higher order terms in beta. But as you can see, this would give us a positive Schur expansion. And basically what we now want to do is like put a crystal structure so that we can also explain these terms. So basically this constant term we get from what we discussed last time, because these would actually correspond to reduced words. So, and the crystal for reduced words are actually the ones for the Stanley symmetric functions. So this we already understand, but we also want to know about these higher order terms. So that's basically what we are going to do today. Okay, so now we have to do the heavy lifting and actually define the crystal. And I should say that we actually currently only have a crystal when the W is 3-to-1 avoiding. So one of the open problems is to define a crystal structure on these decreasing factorizations for the 0 Hecke monoid when for an arbitrary W, not just when it's 3-to-1 avoiding. So what does 3-to-1 avoiding mean? Well, if you write, so if you now view this as a permutation rather than an element in the 0 Hecke monoid, and you write a reduced word for this W, then none of the reduced words should contain a braid of the form I plus 1I for any I, or equivalently I plus 1I, I plus 1. So here are some examples. If you look at 1, 3, 2, 1, well, if we use the relations for the symmetric group, you can interchange the 1 and the 3, right? So to get this. And then you can see that here we actually have a braid. So 1, 2, 1 is precisely of this form I plus 1I, where I is equal to 1. And then using the braid, you can also rewrite this as 3, 2, 1, 2. So this particular word is not 3-to-1 avoiding. If we, however, look at this one, 2, 2, 1, 3, 2, well, remember 2 times 2 is 2 in the 0 Hecke monoid. And you can again interchange the 1 and the 3, but that's basically it. I mean, there are no further relations that you could use. So you can see that there's no braid. You can never see an I plus 1I. So therefore, this is indeed 3-to-1 avoiding. Okay, and I'm going to now define the set of decreasing factorizations for 3-to-1 avoiding, for the 3-to-1 avoiding case by HM star. So star just means 3-to-1 avoiding, basically. So here are further examples. this would be a decreasing factorization, but as you can see, 1, 2, 1 is precisely a braid. So this is not in H3 star. 3, 1, 2, on the other hand, there is no braid and there's no expression that would have a braid. So this is indeed in H2 star. And similarly, this element also does not contain any braid, because the only thing basically you can do is you can interchange the 1 and the 3. So this would also be in H3 star. So that's the case for which I'm now going to define this crystal structure. Okay, so now remember what we did last time. If you want to operate with the crystal operator Fi, in the reduced case, what we did is we looked at the factors I and I plus 1. And remember, I'm labeling from right to left. Okay, so you look at the ith and I plus first factor. And last time what we did is we sort of went through the left factor, the bigger factor, from the bigger to smaller letters. And then we had this bracketing rule. We bracketed a letter here with something bigger, the smallest one that was bigger in the right factor. And basically, we are now going to do exactly the same with one little change, namely, instead of bracketing with something strictly bigger, we are now bracketing with something bigger or equal. Okay, so that's the only change, basically. So that gives us a pairing. And then you just keep going. So you start from largest to smallest, and you do this pairing. And then the way that we define this crystal operator, which I'm going to call Fi star, is as follows. And I think it's best if I actually explain it in terms of an example. So there are two cases. The first case, which is slightly more complicated, and the second case is actually the easier one. So in my first example, this is actually in the smaller case, in the easier case, in the second case. So suppose we have this word, then we now start with the left factor that has only one letter, the 1, and we have to bracket it with something that's bigger or equal. So this will, and the smallest one that's bigger or equal. So we are going to bracket it with the 2. So I've now indicated this by the red things. And then what the F1 operator does, it takes the leftmost unbracketed letter and moves it over. So it just moves the 3 over. And my claim is, since there are no braids, since we're doing the braidless case, you can always move that letter over. Otherwise, it would actually have been bracketed. Okay, and now for the second case, let's do the same thing. So we have two factors. The 7, well, there's nothing greater or equal to 7, so that's unbracketed. But the 5 will bracket with the 6. And the 3 has nothing to bracket with, but the 2 will bracket with the 2, right? Because now we are bracketing greater or equal. So that's what I've indicated here. The 5 bracketed with the 6 and the 2 with the 2. And now we are actually in this first case. If we want to do an F1 operator, now we have the same letter in both factors, the 2 and the 2. And in this case, 2, 2, 1 will become 2, 1, 1. So if you think about it in the 0 Hecke monoid, right, 2, 2, 1 is actually equivalent to 2, 1, 1. So therefore, the two words are still equivalent, because that's basically what we did. We changed the 2, 2, 1 to 2, 1, 1. Okay, so those are the two rules, basically. Either you can just move a letter over if there's no repeated letter, or if there is, you use this rule that I just described. So that gives us a crystal. And here's now an example. I mean, first of all, I'm claiming it's a crystal, but I'm going to show you in a second how you can actually prove that this is a crystal. But now let's assume it's a crystal. And now let's assume we want to actually now derive what this factor is. I mean, how we get the Schur expansion beta 2 S211 plus S22. Okay, so since we have one beta and the reduced length of this is equal to 3, if we want one beta, then we have to look at words of length 4. So one bigger than the length of the reduced case. So here I've listed all possible decreasing factorizations of this particular W with 4 letters and 3 factors. Okay, and the reason why 3 factors is enough, because actually for this Schur expansion, well, the number of parts is at most 3. But I mean, if you're unsure, you can always add more factors in principle. Okay, and if we now use these crystal operators that I've just defined, then you could group all of these factorizations together in this graph. Okay, let's just check. So for example, for this first guy, right, the 3 would be bracketed with the 3, the 1 would be bracketed with the 2. So you cannot actually apply an F1. So that's why there's no 1 arrow coming out of this. But you could apply an F2, which just moves the first 3 over. Okay, and then we've basically grouped all of these into these graphs, which are called crystal graphs. And you can see that we have 3 connected components, right? This big component and 2 components that look isomorphic to each other, except for the labeling of the vertices. And my claim, remember, was that you can read off the Schur expansion by looking at the highest weights. So the highest weights are the ones at the top of the graph, that are the ones where no Fi arrows coming in, or equivalently, these are the ones that are all killed by the EIs. Okay, and now we just have to look at what is the weight. Well, the weight of this is equal to 2, 2, because remember I read from right to left. So this has 2 things in it, 2 things. So this gives us the Schur function S22. And similarly, this one, well, it has 2 factors, 2 things in a factor, 1 thing in a factor, 1 thing in a factor. So that gives us the Schur function S211, but we have it twice, so that gives us this coefficient 2 that I have here. Okay, so as you can see, once you have the crystal and you believe it's actually a crystal, then you immediately get the Schur expansion. And it will also work for the higher order terms, right? You just look at longer words, things with, for this one, you would look at things with 5 letters in it and so on. Okay. Okay, so now we are going to like investigate the forest. And for people who didn't listen to the, okay.
Could we go back to the previous slide, please? I just want to get it clear. So this, with, for example, the 3132, empty 3132 that you have on the leftmost crystal.
This one?
Yes. Now.
Oh, in the, like this one?
Yeah. So that wanted to x1 in terms of, in the monomial, you wrote some monomial for that, right?
Yeah. So in the monomial, this would be x1 squared, x2 squared.
X2 squared. And now what are you, so I am a little confused as to, so there is I can see this, so this whole thing is going to be, I'm a little confused. So that is X1.
Okay. So if you look at all possible vertices, and you now associate to every vertex a monomial. So this one would be x1 squared, x2 squared. This one would be x1 squared, x2, x3, and so on. So if you wrote this in terms of monomials, then you would get exactly, basically the expression how I defined the the Grothendieck polynomials.
But now you're saying,
because this one is precisely in terms of the monomials. So now what I'm saying is we have now grouped all these factors together into this graph, and it's sort of a consequence of the crystal theory that each connected component, so if you sum up only the monomials in this connected component, that would be precisely the monomials for a Schur function.
Yeah, I think I get it finally. Thank you.
Yeah, and the label of the Schur function is precisely the highest weight. So therefore, once you've grouped things together, you only need to actually look at these highest ones, and that gives you precisely the Schur expansion. So does that make sense? Okay.
Yeah, absolutely clear. Yeah, thank you.
Yeah, you're welcome. Any other questions?
Yeah, one more question.
Okay.
Yeah, so the number of brackets decides which M is acting, is it? So you, I mean, because so that's.
You mean here how I label my?
The label 2 is because you start from the right, and you're saying you cannot apply to the first and second term, but you can apply it to the second and third term. Therefore, you write
exactly.
2. Okay.
Yes.
Okay.
Yeah. Okay. Yes. So if you want to apply an FI operator, you look at the HI and HI plus 1.
Okay.
Yeah. And you always count from the right. Okay. So for example, this one, you can apply an F2, but that would act on these two, and the 1 would just move over. But you can actually also apply an F1, so that would act on these two factors together, on the first and the second one. And in this case, the 1 brackets with the 2 and the 3 moves over.
Okay, great. Yeah, thanks. Yeah. Thanks.
Yeah, you're welcome. Any other questions? Okay, so I guess then I keep on going. So now what I want to do is I want to discuss the properties of this crystal. And when I discuss the properties, it will also become clear why this is actually a crystal, or how you can prove that this is actually a crystal. Because I mean, I sort of now pulled these crystal operators just out of my head, right? I mean, I didn't really motivate how we came up with them. But this will become clear once we start talking about these properties. So to do that, I now first want to talk a little bit about a special case of these Grothendieck or stable Grothendieck polynomials, namely the ones that are indexed by skew shapes. So before we were talking about the sigma W, and now here we are labeling them by skew shapes. And there's in fact a different formula for these by Buch in terms of what are called set-value tableaux. So I need to tell you a little bit about what a set-value tableau is. So basically, we discussed a semi-standard tableau last time, right? So you fix a shape or a skew shape, and then you put numbers into the boxes such that it's weakly increasing in rows and strictly increasing in columns. But now, instead of just putting numbers into a box, we can actually put sets into a box. Okay, and now I need to tell you what semi-standardness is, because I need to tell you what is weak increase in rows and strict increase in columns. So that's what I'm going to tell you. So suppose we have 3 boxes like this, A, B, C. And now in this box, we now put a set A. So for example, 1, 5, 7, right? Just that set. And we want to know, well, when would this configuration be semi-standard? So when would this be weakly increasing? So now we have to compare the maximum of the set A with the minimum of the set B. Okay, and if the maximum of A is less or equal to the minimum of B, then we would have weak increase in rows. And similarly, what is strict increase in columns? Well, the maximum of A has to be strictly less than the minimum of C. Okay, so now here's a little audience test. Yes?
Oh, I have a question, but I can wait to ask it at an appropriate.
No, you can ask it.
So what is the W corresponding to nu by lambda?
Oh, yes. So remember that I defined this residue map last time?
Mm-hmm.
And I will recall the residue map again. So basically, you can get from the skew shape to the W by looking at this residue map. So
Okay.
I will get back to this.
Wait for that.
Yeah. Okay. So now here I have 3 tableaux that of shape 3, 2, mod 1, right? So it's the skew shape. And now the question is, which of these fillings are actually give us a real set value tableau?
The first and third?
Okay, so the first, let's check. So if we look at the row, right, we have 1, 2. The maximum of this is 2. And then we have 2, 5. The minimum of this is 2. So that's indeed weakly increasing. Similarly, for the top row, the 4 is less or equal to the 4. And we also have that in this column, right, the 2 is strictly smaller than the 4, which is the minimum of this set. So this is indeed a set value tableau. This one is not, because if you look at this top row, right, the maximum here is 4, but the minimum here is 3. So this does not satisfy this condition. And then, what did you say? Oh, this one actually is also not, because this 4 is bigger than this 3, so it's not column strict. So the only one in this list is actually the first one. Does it make sense?
Yeah.
And as you can see, like we can actually put an arbitrary number of numbers into a box, right? Here I've put 3 things in there. Here I've only 1 thing in there, but it should be non-empty. So you have to have at least 1 number in each box. So you can't put an empty set into a box. Okay, so that's now. So I hope. Question. Yes.
Is there a reason for choosing such fillings because of the 3-to-1 avoiding condition?
Yes. Yeah. In fact, under the residue map that I defined last time, which I will recall again, I hope soon, there is actually correspondence between the skew shapes or these set valued skew fillings and the 3-to-1 avoiding decreasing factorizations. Yeah, so there is actually a correspondence. Yes. Any other?
I have a question.
Yes.
So in the end, would it be right to say that Buch's semi-standard set value tableau and your decreasing factorizations are the same for 3-to-1 permutation, 3-to-1 avoiding permutations, but then
yes,
you have generalized by if you just look at any permutation whatsoever and look at the zero monoid, the corresponding decreasing factorizations, that would generalize this. Is this what you're final saying? So you've generalized by rethinking of Buch's semi-standard set value tableau as decreasing factorizations instead.
Mm-hmm.
You have now, you have removed the condition of the constraint of 3-to-1 avoiding.
No, so far we have not, but we are working on it. So,
yeah. Oh, I see.
But this is the first step for doing that. And so again, if you think back to last week's lecture, so we had these decreasing factorizations for the reduced case, And then I said that if you use the Edelman-Green correspondence, which is some insertion algorithm, then you can actually map from these decreasing factors to normal tableau. So basically, there is this commutative diagram where you have the crystal on these decreasing factorizations, you have the crystal on tableau, and then using the Edelman-Green insertion, the two actually correspond to each other. So this Edelman-Green insertion was a crystal isomorphism. And so for these set value tableau, there is some insertion algorithm which is called the Hecke insertion. And so Monical, Pechenik, Scrimshaw, they have a crystal on the set value tableau, but it was not well behaved with respect to this Hecke insertion. And I will mention that at the very end if I have time. So one point was that we wanted to find some sort of local. By local, I mean the Fi only acts on the factor I and I plus 1, not on, like, you know, everywhere, like on all the factors. So we wanted a local crystal on these decreasing factorizations, and going from this Monical, Pechenik, Scrimshaw crystal, you couldn't do that using the Hecke insertion. So we sort of now translated this Monical, Pechenik, Scrimshaw one on these set value tableau using some other insertion, which I'm going to explain, which is different from the Hecke insertion.
So, so would it be correct to say your main contribution is the local crystal, local kind of operation for
yes
of Scrimshaw et al.?
Yeah, on the decreasing factorizations. Yes.
On the
and that's the first step to actually get it for all the W.
Okay, maybe I'll ask a question further on, but it can wait. So I'll postpone it until later.
Okay, okay. Okay, so now let me quickly define this Monical, Pechenik, Scrimshaw crystal on the set value tableau. So the rules are stated here, but I think it's easiest to actually do it in terms of examples. So suppose we want to apply the crystal operator F2. So on a normal tableau, that would involve the letters 1 and 2, 2 and 3, right? I and I plus 1. And so what you do is every column that you see that has a 3, you put a plus. Every column that you see that has a 2, you put a minus. And every column where you see a 2 and a 3, you put nothing. So because they are sort of already bracketed. So here we see a 3 here, so we put a plus. We see a 2, so I put a minus, and we see a 2, so you put a minus. And then you again have some sort of bracketing rule. So you bracket the plus with a minus. So whenever you see a plus before a minus, you bracket. And you then act on the rightmost unbracketed minus, which in this case is this, meaning you act on this and you make this 2 into a 3. Right, so this 2 here has become a 3. And there's one extra sort of case that can happen. So let me explain that in terms of the next example. So suppose we wanted to do an F4, right? Then how do we assign our pluses and minuses? Well, here we see a 4, so that's a minus. Here we see a 4 and a 5, so we put nothing. So when you see a 4 and a 5 together, you do nothing. And then for the 5, we put a plus. And then the F4 should act on the rightmost unbracketed minus, so that should make this 4 into a 5. But notice that this is a problem, because then you have 3, 5, 4, 5. But now you don't have weak increase in this row, right? Because that would be violated. So what you do in that case is you actually just take the 4 from the right box and you move it over. So the number of things in a box can change under these crystal operators. Okay, so that's the Monical Pechenik Scrimshaw crystal. And so, as I said, so in their paper, they actually posed as an open problem to define a crystal on these decreasing factorizations, which they wanted to intertwine with this Hecke insertion, but they weren't able to do it. So let me now first state that under the residue map that I defined last time, their crystal on set value tableau intertwines with our star crystal. And let me now remind you what this residue map was. So suppose we have a tableau. So this is a set value tableau. Then remember what we did is we labeled the diagonals, right? So the topmost entry will be labeled with a 1, and then this diagonal will be labeled with a 2, and this diagonal will be labeled with a 3. So these are these red subscripts that I have. And then the residue map now makes this into a decreasing factorization as follows. So whenever you see a 3, you take now the sub-labels and put them into the third factor. Okay, so the 3 appears in diagonal 3 and 1, so therefore we have a 3, 1. The 2 appears in diagonal 3, so we put in a second factor a 3, and here the 1s appear in the diagonals 3 and 2, so we put a 3 and 2. So this was the residue map that I already had last time for usual tableau, but it's very easy to upgrade this to set value tableau. And the claim of the theorem is that, well, if we do the Monical Pechenik Scrimshaw crystal on the set value tableau, which basically would change this 1, 1, 2, 3 into 1, 2, 2, 3, then this will intertwine with the residue map. So if I do the residue map here, and now here I do our crystal, which remember said that a 3, 3, 2 goes to a 3, 2, 2, then this commutes this diagram. And this is in fact also one way of how you can show that this is in fact a crystal, because once you prove that, there's actually, if you look at skew shapes, the residue map has an inverse up to certain shifts, and therefore this actually proves that this is a crystal, because they already proved that this is a crystal. Okay, so instead of using the Hecke insertion, you can use the residue map to find this nice rule that we had. But hopefully at the end, I will also say something about the actual Hecke insertion. So instead of using the Hecke insertion, we actually invented another insertion also, which we called star insertion. And again, I think it's easiest to explain this in terms of an example. So this insertion is very similar to the RSK insertion, except for one little detail. So what we do now is, so we take our decreasing factorization, and we now just write it in as a 2-row array, because when I do my insertion, I want an insertion tableau and a recording tableau. So it's best to write it like this. So in the bottom row, I've just basically written the word, right? The 4, 2, 4, 2, 3, 1. And then in the top row, I've just written in which factor it occurred. So the 3, 1 occurred in factor 1. So they both got label 1. And then these got label 2s because they occurred in the second factor, and they get label 3s because the 4, 2 occurred in the third factor. And now here is how the insertion works. So we, again, work from right to left. So we first insert the 1, And it's just first it's just usual RSK, so the 1 just sits there and it's recorded with the 1. Then we append the 3, right? The 3 can just sit there and it's recorded with the 1. Then we put the 2 bumps up the 3. Yes?
What is there a restriction? Is this 3 to 1 avoiding necessarily that you're taking?
Yes, because so the claim is that under this insertion, the recording tableau will be a transpose of a usual tableau, and the recording tableau will be a semi-standard tableau. And when it's not 3 to 1 avoiding, then this won't be true anymore. Yeah, so for the star insertion, we are using that it's 3 to 1 avoiding.
Okay, thank you.
This is another open problem where if you want to work on this, try to find a generalization of the star insertion that also works in the non-3 to 1 avoiding case. And in fact, my students are working on part of this.
Okay, thank you.
Yeah. Anyway, so up to now it was just RSK basically, right? Now we insert the 4. The 4 just sits there at the end. So now in the next step, we are inserting the 2. Okay, so now is the place where something is different from RSK. So in RSK, the 2 would bump the 4. But if a letter appears in there already, so this is basically this case 3 in this insertion, if a letter appears, then basically what you do is you look at the largest consecutive interval of letters. So the 1, 2 is basically this consecutive interval of letters, and the 2 will then bump sort of the lowest number in this interval. So in this case, the 1. Okay, so right, the 2 got inserted, but it produces a 1 in the next row, and then the 1 bumps up the 3. And then again, we just here in this tableau, we just recorded what happened. So as you can see, this is sort of a transpose of a semi-standard tableau, the insertion tableau, but the recording tableau is a real tableau, like a semi-standard Young tableau. And that's a claim. So we proved that will happen if you start with something that is 3 to 1 avoiding. Okay. Oh yeah, sorry. And then in the last step, we insert the 4. So the 4 basically bumps up the 4 because that's the longest consecutive interval. Okay, and then the next thing that we proved is, well, if you look at our crystal on these decreasing factorizations, and if you do the star insertion, so the star insertion, if you look at the recording tableau, actually goes to a semi-standard Young tableau. On semi-standard Young tableau, we already have crystals. And so this very usual crystal operator on semi-standard Young tableau intertwines with the star insertion. So that's the second result that we proved. So here again is an example. Here we have a decreasing factorization. Under F1, this would go to 4 to 1, 3. If you do the star insertion, I think this is the example we just did, in fact. And then the F1 on just the usual semi-standard tableau would change this 1 into this 2. And that's exactly what happens also under the star insertion. So that's our second result, so that it intertwines with the star insertion. And then the next thing that actually also appears quite a bit in the literature for set value tableau or K-theory or Grothendieck polynomials is what's called the uncrowding operator. So that appeared like in lots of different papers, and there are various versions of this. So we actually use this version by Rainer Tenner-Jong in a paper in 2018. And again, I've written out what it means, but it's easiest to understand it in terms of an example. So take a skew set value tableau. And basically what uncrowding means is, well, you have lots of letters in these boxes, and you want to get it to the case when it's just one box in each, one letter in each box. So you start in the highest row that has multiple letters. So for us, that's the top row. And you look at the largest number that is there, that is in a box with multiple letters. So for us, that's the 5. And then what you do is you just take the 5 and row insert it, using usual RSK, row insert it into the next rows. Okay, so if you do that with the 5, well, the 5 will just sit in the next row. And then you repeat. So now you are here, you look at the largest row that has a box with multiple letters, that's this. You look at the largest letter, which is the 4, and then you take the 4 and you RSK it into the next row. So that 4 will bump the 5, and then you repeat. So now you would take the 5, you would RSK it, so that just sits above the 2, and then finally you have this 1, 2 that is in a double cell, and then you RSK that 2, and you get this particular tableau. So basically what the uncrowding is doing, it takes a set value tableau, uses RSK, and it produces for you a skew semi-standard tableau. Okay, and again, it's sort of the natural question, since we have crystal operators on the skew tableau, does that intertwine with these, with the crystal on these? And in fact, that's already in the paper by Monical, Scrimshaw, Pechenik, Scrimshaw. They already proved that this intertwines with this uncrowding. But there's one extra connection. So since we introduced the star insertion, we have the following claim. And again, I'm going to do it in terms of an example. So start with a set value tableau. So here's my set value tableau. Then, right, you can do the uncrowding. So we get this tableau. Or you can first do the residue map. You get to a decreasing factorization. Now you do the star insertion. And remember, the recording tableau of the star insertion actually gives you also a semi-standard tableau, and the claim is that the recording tableau here will be equal to the uncrowding tableau. Okay, so that's the second the second result. And yeah, now finally, let me briefly mention something about this Hecke insertion. So as I said, so in this paper by Monical, Pechenik, Scrimshaw, they tried to intertwine their crystal operators with the Hecke insertion. And when you do that, they even have examples in their paper where under that, the crystal operator basically changes things everywhere in the word. It's very non-local and changes a lot of things. But our claim is that they sort of used the wrong version of Hecke insertion. So let me first briefly say what Hecke insertion actually does. So again, what you do is you start with a decreasing factorization. And again, I write it in terms of this 2-row array. And then you start inserting. And normally it's again just like RSK, right? You insert the 2, then you insert the 3 sits behind. Then the 1 bumps the 2 up. And something happens when you try to insert a letter that's already there. So in the next step, when we start inserting the 3, well, the 3 is already there. And this Hecke insertion actually wants to produce a strictly increasing tableau. So you can't have repeated letters in a row. So if you see something that's already there, then the insertion tableau doesn't change, right? From here to here, nothing changed. But in the recording tableau, we sort of have to record that nothing changed, and we actually put then a second letter into this. So that's what happened. So instead of just the 1, we now have a 1, 3. And that's how you get these set value tableaux using the Hecke insertion. And well, if we finish this example, then you get this as your recording tableau, and that's a set value tableau in general. And then the P tableau is some, as I said, increasing tableau. And so what we showed is, again, that there's a relation between the residue map and this Hecke insertion. And again, it's easiest to do it in terms of an example. So start with a tableau, do the residue map, right? So we get a decreasing factorization. And now take this decreasing factorization and now you do Hecke insertion. So now apply Hecke insertion to this. So we do that. And you can see that the recording tableau is actually equal to the tableau that we started with. So the claim is, if you start with a tableau, you do the residue map, and then you do Hecke insertion and you look at the recording tableau, it's actually the same tableau. And so what was interesting is we noticed this, but the Hecke insertion that we actually used was Hecke insertion from right to left, rather from left to right. And in the paper by Monical, Pechenik, Scrimshaw, they actually always used the Hecke insertion from the left. And yeah, that's why basically they couldn't see that there's actually an easy way to actually define the crystals in the 3-to-1 avoiding case. And just to finish my talk, so what we are currently working on is, well, to upgrade this to the non-3-to-1 avoiding case, so to find the rules that will work. And then once you have the full crystal, you can actually also look at de Mazur crystals. So de Mazur crystals are certain slices of the full crystal, and that should actually help to also get the intersection numbers. Yeah, thank you very much.
Thank you, Anna. Let's thank Anna. You can unmute your mic.
Well, thanks for having me.
Yeah, I have some questions, but not directly related to your talk. So before I ask them, maybe you can see if others have questions. Do others have any questions?
Yes, I do have some, but I can wait.
Okay. Any other questions besides Raghavan and me? Okay, so I guess not. So let's go to Raghavan. Take Raghavan's question first.
Could we see the last but one slide, please? One more, please.
This one?
Yeah, so one question, okay, maybe I have not understood this properly. So you start with this this set valued semi-standard tableau.
Yeah, so now we start with and it has to be of straight shape. It's important now actually that it's of straight shape. So yeah, you start with this, and you first do this residue map that I defined. So the residue map produces for you a decreasing factorization. And, here I've just rewritten it in this 2-line notation. So in the bottom row, I have the word, and then in the top row, I just put in which factor it is. So the 2 was in factor 4, the 3 was in factor 3, and so on. And then we took this and we did the Hecke insertion, which I've only sort of vaguely defined.
I understood the principle, although maybe not the details, but that's not my question so much as.
Okay.
So you have the star insertion on the one hand and the Hecke insertion on the other.
Yes, but here on this slide, I'm only using Hecke insertion.
Yes, I understand. But the question is, so but you said something, this Hecke insertion works only for a particular shape tableau, you said, or a straight tableau. What did you say?
No, so only the theorem on this slide only works when it's a straight shape.
Oh, not skew shape. Okay.
Yeah, because, I mean, that's because the Hecke insertion will always produce something that's of straight shape. So saying that this is equal to what you started with cannot work if you start with something that's skew shape.
But if I do the star insertion on this, I still get the same. If I do the star insertion on the decreasing word,
Yes.
I will get the same tableau, right?
No, so if you, because remember the star insertion actually gives you a semi-standard tableau. So the star insertion doesn't give you a set value tableau. The star insertion
No, oh, I see. But then go back to the, you had that intertwining all the way, this crowding business.
Yes, this stuff.
Yeah. So let me understand. So you have on the one hand set valued semi-standard tableau.
Yes.
On the you have decreasing factorization.
Yes.
And on and you have skew pairs of tableau, right? I mean,
so again, in this case, we are assuming it's a straight shape. And again, the reason is if you do uncrowd, if you start with something that's a skew shape and you do uncrowding, you will get something that's of skew shape. But the star insertion will always give you a straight shape tableau.
So this, but uncrowding itself works in general?
Yes.
Uncrowding itself works. Okay, thank you. I may, maybe for further things, I'll look at your paper. Thank you.
Okay.
Okay, so I had a very general question. So in the case of the Stanley symmetric functions and Grothendieck, stable Grothendieck polynomials, there's really no, we know that there is some representation whose character these are, right? But is there any guess as to some natural construction of the representations of which give rise to these symmetric polynomials?
Oh, you mean for the Grothendieck?
Yeah.
Well, I mean, in principle, having the crystal structure gives sort of like a representation theoretic meaning, right? Because once you have the crystal structure, that actually tells you that this should correspond to a certain representation, in this case of SLN or GLN.
Right. But it doesn't, like in the Littlewood-Richardson case, we just tensor product to representation. So we have a natural realization.
Yes.
The other, so I guess that's. So
I have a question.
Yeah.
So do you know that for the Stanley symmetric function? I don't know. I don't know that. Do you know that?
No, I don't.
Well, for the Stanley symmetric function, we actually had some interpretation in terms of generalized Specht modules. So, but we don't have that in this case, actually.
So where can I find this interpretation?
That's in this 2016 paper with Jennifer Morse.
Oh, okay.
So on the very first slide, I gave the reference, I think.
Okay. So then the other way, going the other way, suppose I do have some strange representation. I know, I have some algorithm to write down a basis and maybe compute how GLN acts on it. Then
okay.
Is it easy to figure out crystal structure that corresponds to it, like starting with the representation to go to its crystal?
Well, if you want to do that, then you actually first have to sort of get the UQ of GLN representation.
Okay.
So you would try to put in a Q also.
Mm-hmm.
Then you would have to construct your bases with the Q in there. And then what you do is you would sort of take the limit Q goes to 0. But the way that Kashiwara actually defined it is, he defined some letters, and then he took the letters mod Q times the letters. But basically that means if you write your bases, you will get some leading term which basically doesn't correspond on Q, and then you will have more terms. And if there is a crystal basis, then having this leading term that doesn't depend on Q actually would be enough to capture all of the things in your that you want to sort of capture in your representation.
So you have to quantize the...
Yeah, I think you would have to quantize, or you would have to guess what your leading term sort of is.
Okay.
Yeah.
Okay. So that's not, is that in your book? I didn't see it.
No, so the book actually tries to totally avoid Q of G. So if you want to do that, then there's another book by Hong and Kang.
Hong and
Hong and Kang.
Okay.
They actually, so they define the crystal theory in terms of UQ of G representations, and they do this construction. They take this limit as Q goes to 0 and so on, and yeah, they basically give that construction. Yeah, in our book we deliberately try to avoid that and just give a completely combinatorial treatment of crystals.
Okay, that was very enlightening. So thanks a lot, Anna.
Okay.
I have one more question. So this generalized spect module, but that's like a symmetric group module, right?
Yeah. Yes.
So going back to Amri's question, for the Stanley symmetric function, is there a GLN or SLN representation theoretic interpretation?
Yeah, so I mean, basically, because we defined the crystal structure on these decreasing factorizations, that gives you the Schur expansion. And
oh, okay. No, yeah. Once you write, no, not
the kind of answer,
but not that way, but directly, so to speak.
Oh, but what do you mean by directly? Like on
Littlewood Richardson, you sort of interpret it as a
tensor
product, as something
more
I see. Intrinsically representation theoretic.
Oh, so you mean like in terms of tensor products and stuff? Yeah, I think that is not known as far as
the representation theoretic, not necessarily tensor product, but essentially, you know, this is the character of this representation, and this is how you construct it.
But let me ask. So maybe I should just look up the paper. But when you say generalized spect module, it's a representation of the symmetric group, right? And
yes,
maybe its Frobenius characteristic is the symmetric function we want.
Yeah, exactly.
So well, that works too, I guess. I mean, so then if you have a spect mod, if you have a representation of Sn, you can probably associate to it some representation of GLN, which would have the right character in some natural way. Should be using
yeah.
Wild
Yes.
duality functors.
Yeah, I mean that would be one way of getting something like that. Yes.
Okay, so any more questions? Okay, so looks like we're done here. Let's give Anna a big applause.